Thank you for taking the time to watch this video. My name is Chen Chen, and I am a Senior Research Fellow in the School of Civil and Environmental Engineering at Nanyang Technological University in Singapore. My primary research interests lie in smart construction, smart manufacturing, and sustainability. Today, I will be discussing production planning and scheduling in precast manufacturing. The construction industry has been shifting towards off-site construction, also known as modular or fabricated construction, in recent years. This innovative approach involves assembling building components in a controlled factory environment before transporting them to the construction site for final installation. Essentially, the construction industry is becoming more similar to the manufacturing industry. By fabricating building components and systems off-site in a controlled factory environment, there are many advantages, such as faster, cheaper, safer, and greener deliveries. However, fully automating production with a carousel system can be costly and expect a good return on investment. We've observed precast factories shutting down in other countries after several years of operation. It's therefore essential to ensure that the factory can remain financially viable. Before addressing this question, let's first review the theory of microeconomics. In the study of microeconomics, companies operating in a perfectly competitive market are referred to as price takers. This essentially means that once the market establishes an equilibrium price for a particular product, companies have no option but to accept it. The only way a company can increase its profit in such a scenario is by reducing its costs. Economies of scale refers to cost advantage that a company can gain by increasing its production scale and becoming more efficient. The result is a decrease in the cost per unit, owing to the fact that the cost of production is spread over more product units. In contrast, these economies of scale occur when a business expands excessively, leading to an increase in costs per unit. This typically happens when economies of scale are no longer effective. Defining the optimal production capacity is a critical task for any organization. Capacity refers to the maximum output a system can produce within a specified period. In general, there are two types of capacity: design capacity and effective capacity. Design capacity is the maximum production capacity that can be achieved under ideal conditions, while effective capacity takes into account the current operating environment and constraints. Capacity planning involves considering multiple factors such as raw materials, labor, warehouse, equipment, output required, and delivery timelines. To optimize capacity, one must ask questions like, do I have enough products? Do I have the right number of employees? Do I have enough equipment? And am I utilizing it efficiently? It's equally crucial to determine the maximum amount that can be produced at peak efficiency. Excess capacity can lead to diseconomies of scale, and it can be challenging to measure a production system's capacity accurately due to its dynamic environment. Capacity is often measured in terms of throughput time, which refers to the amount of time it takes to complete a product from the very first step in the production process to the very last one. In addition, several other types of time can be quite confusing. This slide provides a clear explanation of these different types. Lead time is the span of time between when an order is received and when it is actually delivered. Lead time can be longer than throughput time due to processing in other departments in addition to the production department. Takt time refers to the rate at which a product or service must be completed in order to satisfy customer demand. Cycle time is the amount of time it actually takes to finish a product or service. The cycle time must always be lower than the takt time. If your cycle time takes longer than your takt time, it means your process isn't keeping up with demand. A queuing model can mathematically represent a production system. A queuing model works by having customers arrive at a facility randomly to receive service before departing. Using Little's law, we can determine the queue size, and if it grows faster than the activity stage processes work, it becomes the bottleneck. Bottlenecks can occur due to various reasons. Process bottlenecks can cause project delays, added costs, and unpredictability. To ensure efficient processes, it is essential to avoid queuing or, if necessary, keep waiting time as short as possible. It is a common challenge for companies to have a clear understanding of their optimization goals. Each department has its own set of performance goals based on their respective KPIs. When multiple goals are set, it leads to the creation of a Pareto front with an infinite number of balanced solutions. A balanced solution refers to a compromise between competing objectives without necessarily optimizing any single objective. Defining clear goals is the first step toward success. Lean is a production and management philosophy that focuses on maximizing value while minimizing waste, with the ultimate goal of achieving business success. This approach originated in the automotive industry, with companies like Ford Motor and Toyota leading the way. Over time, Lean has become a widely adopted global management philosophy, offering a range of tools and techniques to help organizations streamline their operations. Today, the integration of digital technologies such as Industry 4.0 is revolutionizing Lean practice and shaping the future of Lean manufacturing and management. In the context of Lean theory, there are two contrasting approaches for managing production and inventory: the push system and the pull system. The push system relies on forecasts and predetermined schedules to plan production, which leads to higher inventory levels as goods are produced in advance of customer demand. On the other hand, the pull system triggers production based on actual customer demand. Products are only manufactured in response to an order or signal from the downstream process. Pull systems typically have lower inventory levels as production is driven by real-time demand, and lead times are often shorter than in push systems. Con-whip is a variation of pull systems, and our precast production system is more like a con-whip system. There are different types of production planning and control system for the pull system. One of them is the Kanban system. When the inventory levels drop to a predetermined minimum threshold, a Kanban signal is triggered, indicating that more inventory needs to be produced or ordered. On the other hand, the MRP is a tool used for calculating the raw materials, sub-assemblies, and components required by a manufacturer to produce a product. OPT and DDMRP are hybrids of Kanban and MRP. OPT concentrates on constrained resources, while DDMRP focuses on critical resources. The aim of the solution is to protect the weakest link in the system. Precast products are classified into 5 levels, ranging from materials to complete units. Level 5 is very similar to Level 4, where the majority of the construction occurs off-site, including interior finishes and final furniture in a volumetric module. The main difference between Level 4 and 5 is that Level 5 modules are complete living units. This slide displays various types of production processes. It is observed that when the number of product varieties is reduced, the production volumes tend to increase. Mass production is considered the most effective when a limited range of standardized products that are either identical or very similar are produced. Cost is reduced with large-scale production. HDB flats are the primary type of housing in Singapore. The Housing Development Board was a pioneer in the use of prefabrication technology, utilizing precast components in flat construction since the 1980s. In every HDB residential project, precast components account for about 70% of the total structural concrete used. HDB has developed a standardized precast building system known as the HDB Precast Building System, which is a collection of 2D precast components that combine to form the entire building system. These standard precast products allow for efficient mass production. When products have large volumes as well as a wide variety, they lie in the 4th quadrant, where the Leagile approach can be applied effectively. Leveraging Industry 4.0 technologies, achieving a Leagile supply chain becomes possible. Leagile is a term that combines the characteristics of 2 approaches, namely lean and agile. The lean approach, which prioritizes efficiency, is more appropriate for relatively stable markets, where the cost is a significant concern. On the other hand, the agile approach, which emphasizes the quick response to market needs, is more suitable for rapidly changing markets, such as the fashion industry. The application of Leagile requires the identification of a material flow decoupling point. The position of this point depends on the maximum lead time that a customer is willing to accept and the point where product demand variability becomes dominant. A Leagile supply chain uses a postponement strategy. The goal of postponement is to delay the customization as late as possible in the supply chain. In order to establish an effective Leagile system, it is crucial to have an integrated production planning and scheduling system. The production planning process involves making the most effective and profitable use of available resources to meet demand. On the other hand, scheduling focuses on managing day-to-day operations within the established guidelines of the planning process. While scheduling is done in advance without considering real-time data or conditions, real-time optimization makes decisions dynamically as new information becomes available, allowing for quick responses to changes. Real-time optimization concentrates on finding the best possible solution to optimize a specific objective, whereas real-time control concentrates on maintaining a desired state or set point within specified limits. In the traditional hierarchical framework, the flow of information is unidirectional, from higher to lower levels, which is similar to a waterfall without feedback. Each level is then solved independently, and optimal decisions at the upper level provide constraints for the lower level. However, the absence of feedback in this hierarchical approach means that any disruptions or changes on the shop floor are not immediately communicated to the higher planning levels. So to enhance responsiveness, adaptability, and overall performance, an integrated production planning and scheduling system incorporating real-time feedback loops is required. And that brings us to the end. I'd like to thank you for your time and attention today.